This is Whiteboard Physics A-Level Lesson 65, Potential Difference and Power. Now there's a potential difference you learn about at GCSE level. I always bring it back to GCSE level. At GCSE level, you learn that potential difference is just another name for voltage. And you learn that because the word voltage seems to be in common colloquial usage. It's something you're more familiar with. Obviously, it's related to electricity. If someone says to you, what's the voltage of that battery? You look on it and it says 1.5 volts. You understand what that means. But no one says what's the meterage when they want to know how tall someone is. They say, how tall are you? And then you say your answer in meters because we're civilized people here. Or no one says, what will be the secondage to boil an egg? Now, you wouldn't say that. You'd say, what would be the duration of boiling an egg? And you might give an answer in seconds or minutes or whatever. So it seems a bit odd that this quantity, we name it for the unit. You see what I mean? You wouldn't say, what's the newtonage of those apples? You'd say, how much do those apples weigh? It's the same sort of thing. So, yes, the word voltage gets used early on in GCSE level, and then you get told, no, we'd prefer potential difference, but there is a good reason for that. So what is potential difference? Well, it is the amount of work that's done per unit of charge that moves through a component or through a part of a circuit. So if I have a lamp, for example, every coulomb of charge that moves through it, if it delivers 1.5 joules of energy, then it's 1.5 divided by 1 coulomb. That's going to be equal to 1.5 volts. Volts are the same thing as joules per coulomb. That's what the unit volts means. And that's fine. The problem with that is that students have this misconception that the charge goes through a power supply, trundles through there, goes through a lamp, and I'll use the signal lamp symbol rather than the filament lamp symbol, and then goes back to the power supply, back to the cell or the battery. So there's a view that the charge picks up some amount of energy, and let's draw this as a 1.5 volt battery. So every coulomb of charge would pick up 1.5 volts there. There's the view that that charge then carries that energy through this circuit and drops it off the lamp, has zero energy when it leaves, and then picks up 1.5 volts again. And we go around and around and around. Of course, that doesn't make any sense. It doesn't make any sense for maybe a few reasons. So one of the reasons it doesn't make sense is we already know from last lesson the drift velocity for the charges, yes, they're electrons, that are flowing in a circuit is really, really low. So it would take so long for the energy to be delivered to the lamp from the power supply. You'd turn the power supply on and then you'd be waiting a day for the light to come on. And that doesn't happen. We know that doesn't happen. The second issue is this implies that there's absolutely no energy left for the charge on its return journey. But if the charge has no energy, how's it moving? It doesn't make any sense to our simple way of viewing things. So obviously, this model is defective. Now, some people will try to get around this defective model by saying things like, well, the electrons are pushing each other around the circuit. And so each electron pushes the one next to it, and that's how the energy is transferred, a bit like a Newton's cradle thing. But that doesn't really work either, because the electrons experience greater forces at smaller distances, which means they would all bunch up and you'd get waves of electrons, pressure waves of electrons moving through this circuit. And that would have a time delay as well that we don't observe. Though it's almost instantaneous. When we connect the circuit, a lamp comes on. Almost instantaneous. In fact, the signal to turn the light on travels at the speed of light. So it's as close to instantaneous as it can get. So our model from GCSE level of potential difference was a bit defective, but we have a better model. And this is the model of potentials. Now, we will cover electric potential in the electric field section in year 13. And we cover it usually just after we've done gravitational potential. And so I'm going to have to give you a bit of a heads up in what seems like a bit of an odd order here, but bear with me, it's going to make sense eventually. I'm going to imagine, and I'm going to do my best to draw this in 3 dimensions. Well, it's not going to be in 3 dimensions, is it? I'm going to do my best to draw a 2-dimensional representation of this situation. We have a circuit, and give myself plenty of room for this. And I'm going to have a power supply here, like this. Then I'm going to have a straight bit like this. Then I'm going to have my lamp. And maybe I want 2 lamps like that. And then I have a straight bit like this again. So there's my circuit. Well, it's an attempt at a 3-dimensional picture of a circuit. What it might look like is a difference in potential along this circuit. We've got, I'm going to use red for this, 0 volts of potential here, and then here 1.5 volts of potential. And all this wire here that I'm colouring in red has 1.5 volts of potential, whatever that is. Now, potential in physics is a technical term. It doesn't just mean something could happen, it has the potential to happen. It is a technical term. It has a particular meaning. This side is all going to be at 0 volts potential, like this. And then we have this interesting situation here with these 2 lamps, where in the middle there's going to be some potential between 0 and 1.5. Maybe we could have 1.0 volts potential there. So what would that look like? Well, in order to try to visualize it, we are going to use a different type of potential that we've got some passing familiarity with: gravitational potential. We've met the idea of gravitational potential energy. Gravitational potential is related to that. In fact, for a particular mass, gravitational potential energy is proportional to, or is equal to, when I say proportional to, the gravitational potential. So, let's try and draw this. I've copied the circuit to help me draw it above, and now I'm going to get some straight line tools out, and then I'm going to try to move my straight line tools away. So nothing can go wrong. I've got a good feeling about this. There's one line. Where's the next one? Delete that. Don't want that. Delete that. Don't want that. That's the one. No, I moved it. Oh, this is going to be difficult to draw. As you can see, it's going to be difficult to draw, but it'll be worth it. When I get this to work, it'll be worth it. Delete that. Delete that. We don't want that line. That's the one. And finally, that one. And everything else I can delete. Right. So I'm going to set up a picture above it where we use gravity as an analog to the electric field. Okay. It's not, of course, they're different. Gravity and electric field are different things. That should be that side. They are different things. Gravity acts on masses, electric fields act on charges. But here we go. There is the same picture as beneath. You see me sketch it out, drawn like this. And then let's get a different color. I'm going to draw this bit a little bit higher. I'm going to draw it 2 squares higher. In fact, we're going for 1.5 volts. So let's do it 3 squares higher. Let's do that 3 squares higher. Then some point in the middle here, I need to be 2 squares higher. So that's 1 square, 2 squares. Then we're down to the bottom, and then we're down to the bottom. And then in a really thick pen, it's all going to make sense. Just trust me. I'm going to go like this, and then we're going to have our battery, which is going to boost us up like that. Then we're going to stay up there. Then we're going to have a lamp, which is going to bring us down to about here-ish. There's our bit of wire, and then another lamp that brings us down to there, and then we're down there. Now that is about as good a diagram for this as I'm going to be able to draw in 3D, and I'm actually quite happy with how that's come out. If you're not happy with that, tough. So let's label some bits then. We've got 0 volts down here. We've got 1.5 volts up here. And here we drop down, so it's quite it's less steep, this bit here. We drop down to this level, which is 1.0 volts. Now, if you imagine we had a roller coaster car on this, we would have to put, there'd have to be work done to lift up to this stage to increase the gravitational potential energy. And the difference in energy between the bottom and the top, we could calculate. We'd calculate that as the gravitational potential multiplied by the mass. Now, we don't know what gravitational potential is yet, but that is true. That is how it works. But here, I want you to imagine that this is a charge moving from an area where the potential is 0 to an area where the potential is 1.5 volts. Potential is just a way of quantifying something to do with the electric field. It's not how strong the electric field is. That's called electric field strength, and that's slightly different. But it's some quantity related to the electric field. So we go from 0 volts of this quantity to 1.5 volts of this quantity, and we are visualizing it like a roller coaster. Because gravitational fields do the same thing. We'd go from 0 to some gravitational potential here because we've been lifted up. We then roll around here. There's no reason for us to stop rolling. We're just going to roll around here at the same potential, and then we're going to fall. And we've dropped 0.5 volts of electric potential. And then we carry on, and then we drop another 1 volt of potential. So the potential difference between the bottom and this middle part here is 1 volt. It's 1 subtract 0. And between the top and here is 0.5 volts. It's 1.5 subtract 1. That is a fairly good way of visualizing what potentials are doing. The reason why we end up back at 0 volts is because we end up back in the same place. And potential is a way of addressing where we are in a field. That's all it does. So let's draw a more exotic circuit. Okay, more exotic circuit. It's worth spending this time on this, okay? You've got to trust me. Worth spending my time on this. Let's copy this. And let's add an extra branch. We're going to add a branch onto this circuit all the way over here with just a single lamp. We could add one with 2 lamps. We're adding one with 1 lamp. Let's try doing it like this. You see why I try to do it in 3D. And let's rub out part of this. Draw my lamp. My lamp's going to go there. Okay. So what's going on here? Well, we've got the same potential. This has to be connected in our roller coaster. That's all 1.5 volts. It has to be. And this bit down here still has to be 0 volts. Can't be anything else. That's still 0 volts. And so what happens on our... Let's get a copy of that. What happens in this circuit here? So just like last time, I'm going to try to I'm going to try to draw it in 3D. So we've got this bit there, we've got this bit there, we've got this bit there. And you can go ahead and try and do this yourself. You know, if you think this is easy, delete. and that one. Right, so let's get rid of these. Yeah, if you think it's easy to draw these, have a go yourself. See how you get on with it. I think it's really hard. Well, there we go. So we've now got this situation. Let's copy this over to here and line it up vertically like that. And then I can delete this bit here because I don't need it anymore. So where's the rest of the roller coaster now then? Well, okay, green. Let's make it thicker. How thick I made it last time. Hopefully I'll make it the same thickness just by random luck. Near enough. We're up there. We're going to end up down there. We've got 0.6 and blue. We've got our vertical parts. There's one there. And we're going to drop in one big step. So we drop, boom, straight down. And so you can see the potential difference is going to be, just like we had last time, 1.5 at the top, 0 at the bottom. So the potential difference across, the potential difference from here to here is 1.5 volts. The potential difference from here to here is 1.5 volts. The potential difference from here to there is 1.5 volts. Because that's what potential is. It's a way of addressing our position within an electric field. And we can represent that in the same way as we do with gravitational fields by looking at heights. Right, that's about as good as I'm going to do for that sort of description. So let's move on to power. And when we look at electric fields in that topic, what I've drawn on this, you're going to go, wow, that's brilliant. And it's going to make a lot more sense. But for now, let's move on to power. Slightly more straightforward for power. Ooh, that's a thick line. Slightly more straightforward for power. We remember from the lessons we've had earlier on that power is just the rate of doing work. And we know that the amount of energy that is being transferred, and I used a W, so I'll stick with a W, the amount of energy that's being transferred per unit of charge is equal to that amount of charge multiplied by the potential difference that the charge moves across. And you can see you can have some charges going up here and other charges coming down here. They don't have to be the same charges, just like they don't have to be the same roller coaster cars. Anyway, okay. So we know that that is true. We also know that Q, the charge, is equal to the current multiplied by the time. We saw that last lesson. So if we plug that into there, we end up with work done is equal to current multiplied by potential difference multiplied by time. And if we plug that into there, we end up with power is equal to current multiplied by potential difference multiplied by time divided by time. The times will cancel, and we end up with our familiar equation, which again is covered at GCSE level. Electric power is current multiplied by potential difference. And let's stop there. That's all we need to know about. That's all we need to know about electric potential difference, and power. There's loads of empty space down here, but the most important thing was this, the idea that we're transferring energy by charges moving from one potential to another, but the potentials are just there. That's what the battery does. It sets up potentials. Just like masses have gravitational fields around them, charges have electric fields around them. Potential is just a way of saying where we are in that field. Good. I'll stop there.